perhaps for you, for instance, it's probably much too physical and the presentation, so I can try to adjust. Okay, so this is joint work with here joint work with these three people, most of it with Rodan Vargas and also some of with François David, and here is completely heuristic definition. I will build on this slowly, but let me flash it to you anyway. So Liouville field is a random field in 2 dimensions with the following probability distribution. So you're taking something which is in this business called the Liouville action functional. So you have a field, scalar field defined on a Riemann surface, and you compute, well, define the action functional like here, and then you try to. There are some parameters which will be more clear in a moment, but there's one parameter multiplying this exponential term, which is called in the physics cosmological constant, and then there is more important parameter is the gamma here, which is multiplying the field, which if I normalize things so that the gradient squared has coefficient 1, then this gamma is a parameter sort of available for the theory. Okay, so where does this occur? It originated sort of in Polyakov's formulation of 2-dimensional formulation of string theory, non-critical string theory, and quite subsequently in 2-dimensional, what is called in physics 2-dimensional quantum gravity. More recently, it was observed that the same theory enters in 4-dimensional supersymmetric Young-Mills theories. Certain partition functions there are given in terms of these Liouville objects, which I will be describing to you. And then it also enters disordered systems, so sort of spin glass type freezing transition and pinning transition. So maybe I comment on that also later. And more mathematically, it enters sort of the mathematical version of the 2D gravity, the theory of fractal random surfaces. It enters integrable systems and what Okunkov calls quantum cohomology. So various sort of theory which seems to be present in various domains, different looking domains. Okay, so as a motivation, let me give just short motivation how it comes in random surfaces, because that motivates.
Maybe you should, before you go on, maybe Pierre or you have a question about what the action really looks like.
I will define it. I will define it.
I would like to look back at the action 1 minute. Yes.
I will define it later more, but.
So the first term is conformally invariant, but the second break is conformally.
Right, you're completely right. So once I need to write, I will write this action more carefully in a moment. Mm-hmm. But you should think about the e to the gamma phi like in a given complex coordinate, the conformal factor of the metric. So this is like a metric term here. So, and to write it for a concrete surface, I have to choose some sort of background metric and then write everything as a conformal factor times that background metric. But at the moment, I'm just trying to write this very intuitively. Okay. I will come back to that, but let me give it 3 slides of motivation. Maybe you can forget about this motivation later if you want, but at least this is the historically how this business entered, and it explains what the gamma parameter in particular is in some of these problems. So this is a story of random surfaces, which one can try to construct in the following way. You think about triangulation. So if you wish, simply show complexes, but just think about the triangulation of a And let's work in the topology of the sphere. That's all my talk will be on the sphere. So triangulation on the two-sphere. Technically, that's called a planar map, but never mind. Think about the triangulation where you try to put a probability distribution on these triangulations. And the probability of a given triangulation is exponential. You weight exponentially with a coefficient mu, the number of triangles, and then you put some extra factor, which I call z beta t. And that is what in the physics is called the matter content. I mean, so you think about quantum gravity, which is the story about metric and of matter coupling to the metric. And concretely here, the matter is put by this coefficient, which is a partition function of a spin system on the triangulation. So if you have a triangulation, you can just, well, you can decide to put nothing there, and that's called pure gravity. And so you just take this Z1, that's the simplest theory. More complicated theory is where you take Ising model there. So this is a partition function of Ising model where on each triangle you put a spin, or you color it by 1 and -1. And you have certain the usual definition of Ising model in temperature beta. And then the fact is that for such models, many such models, you can try to construct a scaling limit, namely taking this beta parameter of the spin system and the mu parameter of the gravity.
Here in this z beta, there's a sum over sigma as well, right?
Yes, exactly. That's missing. Yes, so there should be. These are nearest neighbors. So these are the usual Ising model where the spins of the nearest neighbors are coupled. So you take the near. This is sum over. You put a sigma variable on each triangle, and you sum over products of sigmas on nearest neighbor.
Nearest neighbor near a common
joining a common edge. Okay.
Yes,
Okay. And now it's a fact in many of these cases that there are critical points which one can even explicitly know what they are. So you take beta and mu to certain critical values, whereby this probability measure will be concentrated on larger and larger triangulations, whereby
it's taken as you make finer triangulate.
Yes. So the usual scaling limit. I mean, you measure is. You have more and more triangles, and now you decide that they are smaller and smaller, and you take the scaling limit. Very similar way as you take scaling limit on random walks and stuff like that. Okay.
So all your triangles have to get small.
Triangles get small, and in the limit, you're supposed to get some sort of continuum theory of random surfaces. Okay. And the question is, what is this continuum theory? And here comes Polyakov, who tells us that the limit should be described by a random Riemannian metric. So you take the two-sphere and put a random Riemannian. Let's take two-sphere here, so the extended complex plane, and take the Euclidean metric times exponential of, well, it's conformal factor. Okay, so that's a positive thing.
And on which model you.
That's the next slide.
Oh.
Okay. So Polyakov told us that we should think about the limit in terms of such a random Riemannian metric. And then the question is, of course, if it's random, what is the probability law of this metric? I.e., what is the probability law of this function phi?
So wait a minute, you're describing triangulations, and you have a partition function, you have a weight on triangulations.
I have a probability.
So why is that described by a metric?
Okay, so I wanted this to be just a background, okay, but let me. Yes, so there's a long story here. So given such a triangulation, you can put a conformal structure to it. So you can decide that every triangle has area 1 or area epsilon, for instance. And then you can map it if it's a triangular sphere. You can conformally map it to the sphere, and that way you get random metric if you take the graph distance on the triangulation. you get the random metric on the sphere. Okay, and then you can try to take a limit of this thing.
I don't understand what the conformal structure was if you have a triangulation.
Okay, so take a triangulation and decide that every triangle is equilateral.
In flats?
Yes, flat equilateral, but of course you can have million triangles joining at the vertex, so you get curvature. That way you get curvature singularities, but in the limit you expect to get something in the continuous limit. Okay. Now we went back in even. Okay.
And speaking of limit, what do you measure to speak of a limit?
That's a very good question. So in this case, I could, for instance, try to do the following. You map it to the two-sphere, and you have this random metric there. You have also a random volume, right? And you could ask, does this random volume, once I approach in a suitable way this critical point, does the random volume converge to some random volume on the two-sphere? And then you can ask whether the random Riemannian metric converges. And these are mostly open questions. Only in the pure gravity case it has been proven actually that not exactly what I'm describing here, but the graph metric, if you view the triangulation as a metric space, random metric space, then under Gromov-Hausdorff convergence, this random metric space converges to a certain continuum object, which is very explicitly known. In the case where you put nothing, in this case, this pure gravity case, this is a theorem by Le Gall and Mirmont, and it's called the Brownian map.
Sorry, there's also a sense of convergence of the randomness. Is it converging almost surely, or is my problem?
Right. Okay. Okay, we're getting further and further. So in their theory, you have convergence. So you have a metric space, which is you have a random metric space, and in the space of metric spaces, there's a notion of convergence, which is called the Gromov-Hausdorff convergence, and then these metric spaces converge. At least in probability. Probably, yeah, I think in probability. But this is not really, I mean, I'm getting further and further what I'm really going to talk to you about. But, all I wanted to motivate you was a little bit the Liouville theory, namely what is the probability law of this phi here. And these people in '88 gave one the answer, again on a heuristic level. They say that the limit, this random object on continuum object, this thing, the phi should be the Liouville field, the one which I heuristically defined you in a moment ago, where the parameter gamma depends on what kind of system you put on the graph. Okay.
Like an icing or
yes. So for instance, and there's a relation because these are spin systems. They have critical points which are scale invariant, and there is a number called central charge attached to them. Technically they are conformal field theories, and they have this central charge. And there's a relation between the central charge of the spin system and the gamma of entering in this Liouville field. It's just a relation like that, okay? Never mind too much about it, except that this Q enters all over the place, so it's a certain combination of gamma and 1 over gamma. So if you put no matter there, you get gamma equal this number, Ising model that number. If you put the uniform spanning tree on that, you get gamma square root of 2. If you put the Gaussian free field on the graph, you get gamma equal to 2, and then there is zillions of other models. Okay, so that's called the KPZ conjecture. Okay, Knizhny-Polyakov Zabalczyk.
In the Liouville field there was a mu also.
There's mu, yes. The mu, as it turns out, plays a very little role here, except it has to be non-zero. Okay, there's a simple scaling how you can change, and that's not so surprising if you look at where do I have this? If you think about that, you're integrating over all functions here, then if I just consider constant functions, and I can, if this measure were sort of invariant under shifts of constants, then that would just shift the mu. Okay.
So can I say Liouville theory is a 2D version of Schramm-Loewner evolution?
No.
No. Okay.
No, Schramm-Loewner evolution is describing, for instance, Ising model. It's describing the continuum limit of the phase boundaries of the Ising model. These are random curves on the plane, and it's a concrete description of those things. Now, the Liouville model is supposed to describe the Ising model on a random surface. Okay. So here's the other part of the KPZ conjecture. So I told you what was the gamma C relation. For instance, if you take the Ising model like we did, and suppose you're studying the Ising model just on the usual plane, the scaling limit of the Ising model, and let me denote sigma tilde the scaling limit the Ising model on this random surface. Then the KPZ tells us that these two random objects are related to each other by a very simple relation, namely, in law, this is a random field and those are random fields. The first is just the product of the other one times this Liouville factor. So to go from the non-random case to the random, non-random surface to the random surface, you have to multiply by this exponential of the Liouville field, and these are independent fields. Okay. And there is a famous relation which tells you what parameter alpha you are supposed to put here. That's called KPZ relation. And in the case of Ising spin, for instance, you have to take such an alpha, and then the conjecture is that that's the relation between these two random fields. Okay. And there are similar statements for all conformal field theories with C less than 1.
Now, I think it's easier to compute the partition function for the Ising model on a random, or a Potts model on a random scale.
Yes, it is easier to compute. So
on a random map than it is on a deterministic one.
Right.
Right. And
right.
Then this tells you how to go back and forth.
This can also be used then going back and forth. Exactly that, and that was done in physics a lot in the 80s.
And just to be clear, in this 88 paper, these are conjectures.
All of this is conjectures, okay, and I put it here only just to try to motivate what is the gamma parameter, and in particular motivate what is the gamma parameter, and in particular also motivate what one should be interested in computing in the Liouville theory if all these conjectures were true. If you are interested in, say, correlation functions, which you usually are, then you should be able to compute then in Liouville theory correlation functions of these exponentials of the field with various parameters multiplying them. Okay, and so heuristically you're supposed to compute such an integral. In physics, these exponentials of the scalar field are called vertex operators, and so you're supposed to be able to sort of prove that such things first of all exist, have nice properties, and maybe even to calculate them explicitly. And that's the goal of this talk, which probably is not going to be achieved, but anyway. So to try to start now rigorously first defining what do we actually mean this thing, okay? So let me try to be a little bit more precise. So there's one part of it which is obvious. There's exponential of a quadratic thing times this mysterious d phi. So that we should try to define probabilistically in terms of what is called the Gaussian free field. Okay, and there's many ways to describe it, but here is one. So you can view the Gaussian free field as a random sum of eigenfunctions. Namely, take the eigenfunctions of Laplacian. Okay, you take the Laplacian of the sphere and call the eigenvalues lambda n. There is a discrete number of them, a discrete infinity of them, and then you take take the coefficients independent, mutually independent Gaussian random variables with variance 1 over the eigenvalue. Okay? That's the definition of Gaussian free field. There's one problem here. There is one eigenfunction which has 0 eigenvalue, namely the constants. That's clearly annihilated by the Laplacian. So that I can't use here because it's 1 over 0. Okay? So the constant plays a very special role here. It's what is called the 0 mode here, and it has to be treated separately. So an obvious way you try to define this would be the following. If you have some functional of this field phi, like what we are interested in, then define it, the expectation. I use brackets here because I will have expectation also. So define it with the following formula. You insert to the phi this Gaussian free field, the sum of n from 1 to infinity, plus the constant, which is the one which is missing from here. Okay? The integrate over the constant, that's in spirit of this measure here. You integrate over the constant and take expected value over this random field psi. Okay? And then the Liouville term is here. Okay?
This is
Does it look
essentially saying that a Gaussian with infinite variance is just a uniform distribution.
Yes, but of course it's really not a probability. Lebesgue measure on the R is not a probability measure. Okay.
So yes, do you have to divide by something?
No, I'm not. No, here I'm not dividing by anything. Okay. Well, actually, you have to. Once I really define you exactly, I have to put number 2 in front of it. But that's all. Okay.
So what I mean, it looks like it has to be infinity.
No, well, that's a good point, and we come to that in a moment.
So
Okay.
there's some Gaussian method.
There's a Gaussian part, namely the psi. That's a Gaussian random field, right?
Gaussian with mass 1.
Gaussian, no, this is Gaussian with 0 mass. I mean, psi n are functions, eigenfunctions of Laplacian. So this is a random function of the sphere. And the E refers to taking average over those random functions, namely average over those random coefficients.
Yes.
Okay.
Independent.
These are independent, independent.
Each a Gaussian low.
Yes.
Yes, each has a
Plus
Gaussian
one.
with mass, this mass,
Oh.
the inverse of the eigenvalue. Okay.
So it's the inverse of the eigenvalue.
Yeah. So think about taking variance of 2-point function, psi, expected value. Since these are independent, you get basically sum over 1 over lambda times eigenfunction. So that gives you a green function of Laplacian. Okay? So that's the motivation here. That's why it should be this, because if I do this, then the variance is the green function of Laplacian, and this is Laplacian here. Okay. Okay. There's a slight catch here. Once you define it like I did here, this Gaussian free field, it's not actually a function. This series doesn't really converge. Namely, if you compute the variance of, that's the inverse of Laplacian, and the inverse of Laplacian in 2 dimensions goes like logarithm of the distance, right? So in particular, if z is z prime, this variance is infinite. Okay, so it's not a random function, but it's actually a random distribution. It just barely fails to be a function. Okay. So then the question is, what does it mean to take exponential of a random distribution? That's of course a non-trivial question a priori. This is well known to anybody who has worked in quantum field theory, because this is, after all, a very simple, super renormalizable quantum field theory in 2 dimensions. So the part of the audience who has worked in quantum field theory knows that it just should Wick order. Okay, and in practice, it's the following: you regularize it, so convolve it with some approximate bump function with a parameter epsilon, which takes to a delta function in the limit. So then you have a smooth function, take exponential of the smooth function times gamma, and renormalize it by multiplying the whole thing by a number, namely dividing by the average. So since it's Gaussian, the average of e to the gamma psi is given by just such a factor. So this number here diverges, right? When epsilon goes to 0, it goes to infinity. So in the limit, you are multiplying it by 0. And now the fact is that this object converges not as a distribution, not as a function, but as a measure. So if you take this density type Lebesgue measure, then in the limit, almost surely in the realization of the psi, this guy converges to a measure, Borel measure on the sphere, in the sense of weak convergence of measures. So for almost every realization of psi, it converges. And the limit is called Gaussian multiplicative chaos. This measure was originally probably introduced, goes back to Mandelbrot, but this particular convergence was proven by Kahan in '86. It's called the Gaussian multiplicative chaos on the sphere. You can do it on the line. The sphere is just my example, but you can do this in many other cases. Okay. So this is a random measure. It's a rather interesting random measure which has been studied a lot in probability. It's multifractal measure. I won't go more to that. What I mean by that unless you insist. It has, for those who know what this is, it has something which is called the freezing transition at the particular value of gamma, which is gamma equal to 2, which corresponds to C equal 1 of this conformal field theory. And what
you did not use gamma yet.
Gamma is all the time here, okay?
Oh.
Yes. So Kahan showed that for all gamma this converges.
Yes.
But now the question is whether the limit is non-trivial, okay? And the slightly surprising answer, if you never have seen it before, is that the limit is non-zero if and only if gamma is less than 2. When gamma is 2, the limit is actually 0. Okay? And that's a very important borderline in all these theories, this gamma equal to 2. And for those who know about this, what is a freezing transition, there is a freezing transition there in the sense that if you can renormalize it so that also at gamma bigger than equal to 2, you have a limit, but the limit freezes to what it's at gamma equal to 2. This is a side remark.
Singular limit.
Yeah, the limit becomes a singular measure, and it gets actually concentrated on the maxima of the field, well, minima of the field. Yeah. It has also something which I will refer in a moment. So it has slightly different modulus of continuity than the Lebesgue measure, and one implication of that is that if you integrate a diverging function like 1 over x to power a, well, for Lebesgue measure this would diverge when the exponent is bigger than equal to 2, right? Here there is a quantum, what one calls the quantum correction. It diverges only when the exponent is bigger than equal to 2 plus gamma over 2. So when gamma is 0, we have Lebesgue measure, but when gamma is bigger than 0, it has the.
What does modulus of continuity mean?
Oh, okay. Let's take it mean just this. Okay, it's a technical definition in analysis. Modulus of continuity of a function or a measure.
Like a Hölder exponent.
Yeah, like a Hölder exponent. Like a yes. So
It's a measure, not a function.
yeah. So then you look at volumes of balls, okay, and ask how they scale. Yeah. But let me just ignore the name modulus of continuity and ignore quantum dimension. Just to remember that this is the condition for singular things to not to blow up. Okay.
So it's more regular than Lebesgue?
In that sense, yes. It's living on a much smaller set. Yeah. It lives on a set with houses of dimension less than 2, depending on gamma.
To me, that would mean it looks less regular, but.
Well, I mean, volumes of balls scale differently. Okay, yeah, you can imagine that, right? Okay, so now we can finally define it by the following formula. So I integrate over the zero mode. I take value, expected value in the Gaussian free field. I put the Liouville term, which we had here. So gamma e to the gamma phi. There is phi was a sum of the zero mode and the Gaussian free field. And the Gaussian free field part we interpreted as the multiplicative chaos. So here it is. Okay, I compute the volume of the sphere in this random measure, multiplied by these factors here, and here you see how the zero mode couples to the mu. Okay, and then there's a slight catch because to do this on the sphere, I really, as you said in the beginning, I should choose a metric on the sphere, reference metric on the sphere, and once you do that, you get an extra factor like that. And if you are interested in that, it's this small text here. So you should really use the volume. Take a smooth metric on the sphere, say the round metric, for instance, and take the volume form of the smooth metric, which is just the metric times z, and then you have to add to the term which we had already, the Ricci curvature term. So this is a Ricci curvature term of the background metric, and there's a linear term in phi which you have to add it once you do it correctly. Okay, and then once this term, because of Gauss-Bonnet, gives you something which depends on the genus of the surface, and in the case of sphere it comes like that. Okay, I don't think I want to go more to this story, but believe me, that's how it goes. Okay, and here is the definition. Then you have Gaussian multiplicative chaos on the sphere, and this is the integral, and there is this extra factor here. In the case of torus, this factor will become 0. In the case of surfaces bigger than genus bigger than 1, this factor comes with a plus sign. Okay. Okay, so the exponential. So that's the definition of the Liouville expectation, these brackets. Okay. Now the question is, for what kinds of capital F's this makes sense, because as John noticed, this doesn't look too harmless because it's exponential of minus of positive. So this is bounded by 1, right? But of course there's an integral over dc, and especially if you look at this factor, it converges very well when c goes to infinity, but not that c goes to minus infinity, right? Okay. So we are interested in the exponential fields. They have, of course, the same problem that e to the alpha phi is not a function, so you have to renormalize exactly in the same way. So let's not anymore pay much attention to that.
That expectation is with respect to the Liouville theory or the free field?
This is Liouville theory. The bracket is always Liouville, and E is the free field.
No, but the renormalization, the E is the free.
E is always the free,
okay.
Yeah, and bracket is Liouville. I try to be consistent.
Yeah,
okay.
fine.
Okay. So, question: does this limit exist? Answer: it exists, then it's non-trivial if and only if all these alphas are less than q, and some of them is bigger than 2q. I will try to explain these things in the next 5 minutes. Recall that q depends on gamma. These bounds are called Seiberg bounds, and they were basically noted by Antti Seiberg in the early 90s. And if you look at them, in particular, it says that since some of them has to be bigger than 2q and all of them are less than q, then at least you need at least 3 of them, right? So, answer to John's question, this correlation functions exist only if I have at least 3 guys there. Okay? That's an interesting thing, which if you have ever thought about, well, let me come back to that in a moment. But let me first tell you where they come from. So here is the definition once again. If you look at the constant mode, you can do this integral explicitly, right? So the C occurs because you have the alphas, and then there was a 2q, which I didn't explain you very much. So there is such a thing. And e to the c here. So that's an explicit integral. Okay?
So is that gamma times c or
Where?
In the exponent?
Gamma times c here. Yes. So the integral converges if and only if when c goes to plus infinity, this goes to infinity, right? So this looks pretty good, yeah? But when c goes to minus infinity, there is nothing coming from here. And this diverges unless this thing here is positive, right? So it converges if the sum over alpha is bigger than 2q. And if it converges, then then the result is some explicit factor times exponential of inverse of this thing to certain power, and the power comes just from the change of variables here, like that. Okay. So if sum over alpha is bigger than 2q, this is actually the result is given in terms of expected value, just in the Gaussian free field of these exponentials times 1 over the multiplicative chaos. Okay. So this explains the first claim here, that this has to be bigger than 2q. Where does the other one come from? That comes from the following. If you look at what I'm supposed to compute here, expected value in the Gaussian measure of this multiplicative chaos guy times exponentials of psi. I can get rid of this by shifting the field. Yeah? If I shift the field by such a factor, I can get rid of, in the Gaussian integral, technically it's called the Cameron-Martin theorem, but I think you can more or less see what's happening here. It's a change of variables. I shift the field, so then the multiplicative chaos then picks up such a guy, okay? If I shift psi by that, then that's how it comes, exponential of minus log alpha I. And the result is that Liouville, here is an explicit expression for them. Once you do the shift, you get some product of zi minus zij's. So there's this gamma function and the mu dependence here, something which looks like doing a Gaussian free field calculation here. And then expected value of now integral of 1 over z minus zi gamma alpha I of multiplicative chaos.
That's your random measure.
This is a random measure psi, m there.
That's your Liouville. Oh, that's the.
This is the e to the gamma psi times Liouville.
With the free field.
With the free field, yes. So the Seiberg bound A comes from the following. I told you that this has modulus of continuity, whatever it meant, that this diverges if gamma alpha I is too big. And the constraint was that gamma alpha I was supposed to be less than gamma times q. So this converges almost surely. This is m integrable here if and only if alpha I is less than q. There's a lot of analysis here to actually show that everything works.
It's just like scaling the way you explained it.
It looks like scaling, but of course you have to do a little bit of analysis, probabilistic analysis to do this, because they are okay. But that explains where the Seiberg are. So the alphas can't be too big. Okay, so interpretation. So what did we get? The Liouville correlation function is expected value of z to minus s times explicit factors, which let's forget about them now, of such an integral, where psi is the random Gaussian field. You can interpret it in various ways. One way is to say that the z is some sort of you have a random geometry, you have a random volume, exponential of gamma times psi times the usual volume. And so there's a random volume element, or random metric, if you wish. And then there are the extra terms. These are conical curvature singularities at alpha I. Exponential of sum over log z minus zi times alpha I, gamma. So I can think about this, that I have the random metric coming from the Liouville, and then the vertex operators produce conical curvature singularities there. Does it sound familiar?
So
If you think about ordinary geometry and you try to, what is the Liouville theory? Liouville theory originally was done by Liouville. What was he doing? He wanted to solve the Liouville equation, namely the Euler-Lagrange equation of the action functional what we had. That equation is an equation for negative and its solutions are negative curvature metrics on the surface. That's how it entered uniformization theory, okay? We are in the sphere. What are the negative curvature metrics on the sphere?
singularities.
They have to have singularities. How many? At least 3. And they are conical, and the cone should have non-zero angle. That means alpha I has to be less than q, where q is the q classical, which is gamma equals 0, limit of that, okay? So there is so in that case it has to be less than 2. So classical theory says that you have negative curvature metrics on the sphere if you put at least 3 singularities which are not too strong. The probabilistic theory says correlation functions are well defined if you put at least 3 vertex operators with weights alpha I, whose sum has to be bigger than something, and they shouldn't be too big.
So
Complete parallel.
So the vertex operators give you
Yeah.
singularities.
They give the singularities.
Which you need in order to have a uniformization.
Exactly, and actually, if you wanted to do the from Liouville equation, the classical Liouville equation, the metrics on the sphere, you should put these vertex operators. You should add these singularities, and then in the complement you can have negative curvature in the metric. So it's completely parallel here. Okay, so that's sort of one. There's a completely different way to think about what this end result is. You can think about it as a random energy model. You think about z being a location of a particle moving on the plane, a thermal particle moving in a random potential, where the potential is this psi, the Gaussian free field. Okay, and this I view as the Gibbs measure in inverse temperature gamma. And then what is happening here is that there's a random potential, and then there are sort of deterministic singularities, but attractive points at zi's. Okay, and then what happens here is that when gamma is too big, then there is a transition from a delocalized phase, where delocalized phase the particle is looking at everywhere in the potential, and in the to some sort of glassy phase, where the particle is basically just located at the minima of this potential. And then there is a separate thing about these potential wells. If they are too strong, then the particle gets just stuck into the well. There's a pinning transition at the point. So
This is just a theory of n particles you got there, right?
no, one particle.
One particle.
One particle moving.
In this background.
Moving. You have this random potential, and on top of that you have these deterministic potential wells.
Yeah,
Okay.
Yeah, it's a log interaction. Right?
It's a log. Yeah. Okay. And that way, okay, there's a lot of work. Ledussal, Santa Chiara, and people like that have been using sort of Liouville theory to study this problem. Okay, starting from such formula.
Is there a dynamical theory for it too?
Oh yeah, people have also looked at dynamical. I mean, you can, yeah, there's a lot.
Is there a nonlinear version that would arise as a mean field model of some interacting electrons in the background?
Non-linear.
Well,
Oh.
you said it's a free model in the background, right?
You want to replace the psi by non-Gaussian field.
Yeah.
Well, I mean, okay. I'm not completely sure what if anybody has look at that, but this is a simple simple model for the freezing transition. Maybe I try to get at least to something, right? Shall I continue? Is it so far clear? Okay. So I've motivated you how this heuristic thing can be actually reduced to something quite well defined. Basically, expected value in this random exponential of the random Gaussian field, and then such things.
And
okay.
that's a random thing, right?
That's a random thing, and we are interested in one particular moment of it. Remember, S, I didn't stress it maybe enough, but the S is a function of these alphas. Okay.
Okay.
Okay. It was just this sum of alpha minus 2q, the thing coming from here. Yeah. Okay, but it's not any old model. I mean, it's a particular expectation in this Gaussian multiplicative case, but it actually has a secret symmetry of its own. After all, the Liouville action functional has conformal symmetry. That's how it originally came from. Okay, and indeed, this random field, what we have constructed, is actually conformally invariant in the following sense. This object, this vertex operator correlation functions, once you look at them, take a Möbius map of the sphere, then they transform in the natural way as conformal tensors. Okay, computed at transform point, you get Jacobian to certain powers times the guy before, and the powers are certain functions of this alpha here and the gamma.
They need to be linear fractional. They can just be.
What?
They need. Is this Möbius map linear fractional or?
Möbius, yeah.
So you mean that? Okay.
Yeah, fractional linear.
I can't take a conformal map and do the same thing.
That's the same.
No, that's the same. On the sphere, those are the only conformal maps on the sphere. Yeah.
Okay.
Okay.
Yeah, sure.
You're asking about local conformal
Yeah, yeah.
invariance. There's that also works here, and that's a small text here. So that's described by conformal word identities.
Yeah, that's what
Okay, the infinitesimal conformal transformation. Those can be proven. We prove them also, and also there's something called the Weil anomaly formula. Namely, how does this thing depend on the background metric you put there? Answer: almost nothing. There's a explicit factor when you vary the metric, which comes multiplicative in front of the correlation functions. It's well-known formula, and in all these things enters the central charge. You get the Virasoro algebra here, and you get central charge, which is the central charge of Liouville theory. It's given by this number here. Okay, and something called the BBC equations also hold, so let me not go to that now. Okay. So what would you, okay, so we have now gotten a conformal field theory. Correlation functions, we know when they exist. They are conformal invariance in that way, and all kinds of nice things. What should you do with it? Okay, well, that's the topic of conformal field theory, and there is a completely there is a approach to this business started by these three people quite a while ago, and they have the following sort of axiomatic picture of what conformal field theory should be, and they say that it's determined by certain data, namely a number, which is concretely it's a central extension of the Virasoro algebra, called central charge. Then something what they call spectrum, namely the set of primary fields which transform like what I had here, tensors under these Möbius maps. Okay, so transform like tensors. So in Ising model, for instance, the spin and energy are primary fields. Okay, and then they said that on top of that, one needs to have 3-point functions. Namely, you take these primary fields, three of them, and consider the 3-point function. Since the thing is Möbius invariant, then it's obvious that the spatial dependence is completely explicit. You can move these points to, say, 0, 1, and infinity, and the others are determined. So the data you need is this number, Cij k, of taking 3 primary fields with at those points. Okay.
And your alpha JK are going to be your IJK are going to be your alphas that you have.
In Liouville model, they will be that. Okay, but this is the general picture. Okay, so in Ising model there are three such, namely the spin, energy, and then the identity. Okay, and the basic postulate of these people is that once you know this data, see the spectrum and the structure constants, then all the other correlation functions are completely determined by recursive formulae, explicit recursive formula, which go under the name conformal bootstrap. Okay, I won't go to that, but that's their picture. Okay, so you need to know these things. Now, in their paper, they found these numbers for the so-called minimal models, for instance, the Ising model, but they failed to find them for the Liouville theory. Found meaning that this is a theoretical physics paper, okay, but they found the explicit formula. Okay, and as a consequence, Polyakov in his autobiography wrote that he viewed that time conformal field theory like he developed it as an unsuccessful attempt to solve the Liouville model, which is a pretty funny way to put it, because conformal field theory sort of was one of the biggest things in physics those times. Now the spectrum of Liouville also was conjectured. What are the primary fields? They are supposed to be these e to the alpha phi's with particular alphas, namely certain complex alphas given by this formula here. It's the spectrum.
So your alphas can be complex.
In the random, in the 2D gravity, they are always real. Okay? But the spectrum, which is a technical term having to do with eigenfunctions of certain Hamilton operator, they are actually complex. Like spectrum of Laplacian is e to the I. Okay, so that's the reason of the P, IP there. In the mid-90s, these people gave explicit formula for the Liouville structure constant. So what is we are supposed to compute these numbers, alpha 1, alpha 2, alpha 3. Okay? They gave an explicit formula with a rather amazing derivation, which they then commented that it should be stressed that the arguments of this section have nothing to do with derivation. These are rather some motivations, and we consider the expression as a guess, which we try to support. Okay, so ever since this formula, what they gave, it's here, has remained a bit mysterious, but it's explicit. There's some prefactor, namely the cosmological constant, what we were talking about. Remember that mu to power s is basically what we had in already. And then there's some gamma business, and then a special function on this alpha. What's
that function called?
It's nowadays called Zamolodchikov epsilon function.
What is Zamolodchikov epsilon?
Epsilon. I think this is epsilon. Okay. It has various definitions, and it's a function which occurs in number theory also. So you know probably more about it than me, but anyway, it's an entire function with simple zeros, so that actually the resulting function is a holomorphic, actually meromorphic function of all the alphas with simple poles on the real axis, discrete points on the real axis, depending on these gammas here. Okay, never mind this particular location, but it's completely known. So what did we find? We find that the structure constants are given explicitly by such an integral, the multiplicative chaos, and the 3 points, one at origin, one at 1, and one at infinity. I write it a little bit sort of intuitively. So we have this probabilistic expression, which is completely well defined, but the question is that is it actually given by the DOS formula? Okay. Some of you might have seen similar formulae. There's a famous formula by Fyodorov and Bouchot going back to the 20 years ago or something, where you look at the multiplicative chaos not on the sphere but on the circle, and its moments there have also explicit formulae. Turns out that this formula, which has been sort of a conjecture waiting for a proof for a long time, actually also follows from Liouville theory in the same way as we show here the DOS formula that was recently shown by Guillaume Remy. You just have to take Liouville instead of the sphere on the unit disk, and this formula follows. It's a DOS formula on there. Okay, so the question is, does the probabilistic expression we have here, is it given by this crazy formula? And how would you prove it? Okay, there's a small dilemma here. As I showed you, the DOS formula is defined everywhere on C3 minus certain poles on the real axis. And in particular, it turns out for generic real alphas, it's non-zero even if the alphas are bigger than Q. You remember that the probabilistic expression was identically zero whenever alpha was bigger than Q. That was the pinning transition. Okay, so there seems to be.
So the DOZZ has a broader range, you're saying?
Well, DOZZ is explicit formula, and it's certainly non-zero there. And the probabilistic, the limit of epsilon go to zero of regularized correlation functions exists, and it's non-zero. It's non-zero only if alpha i's are less than Q. Okay, so there clearly is something strange here. Okay, so the answer is the following. So let me take real alphas which satisfy these Heiberg bounds, which guarantee that these guys exist. Then they are actually given by this formula, DOZZ formula. That's the theorem. And the DOZZ formula is the unique analytic continuation of this probabilistic expression to C3. So upshot is that the renormalization and the analytic continuation don't commute. Okay, so if you try to do the limit outside, you get zero, but the analytic continuation of the guy which you construct on which is non-trivial is not the limit of the probabilistic guy, which is interesting. Okay. Small remark: one can renormalize this so that you get non-zero result. That's possible to do. However, there is this freezing and pinning transition point where things sort of there's a non-trivial limit, but it doesn't satisfy DOS. So that's not the right way to try to define them.
So
the right
freezing means something become constant?
I'm sorry?
Freezing means something become
Freezing means in this business there's a temperature, high temperature where things are sort of understood, and then comes the critical point, and then things become constant, so they don't anymore depend on temperature except for very trivial ways. Okay.
So were DAWs working on R, or?
I'm sorry?
Were DAWs working on R or on C3 or what?
No, when you have the Seiberg bounds.
C is my probabilistic thing, which I defined you only for real alpha satisfying Seiberg bounds. The real alphas, but real alphas less than Q. Okay, that's how C was defined. This is defined everywhere. Okay, and for the ones where this is defined, I agree. And then the analytic continuation of this guy is this. That's the claim.
So in other words, the C alphas have an analytic continuation, but only after you've taken the continuum limit.
Well, they are analytic also. They are analytic before you take the continuum limit, okay?
Yes.
But these analytic functions converge to the right thing when you are on the Seiberg region, in the neighborhood of the Seiberg region, but to the wrong thing in the.
And can you take the alpha a little complex also or not?
Yes, that's here is. I think it's finished, but let me give the structure of the proof. So the first thing is to show that they are actually, the probabilistic things are analytic in a neighborhood of the Seiberg bound. That's the first thing. That's already non-trivial. You might say that since it's an expected value of e to the alpha phi, right? You might say that, okay, I can put an I beta here and take absolute value and less than e to the alpha phi, right? doesn't hold because of the renormalization, because the e to the alpha is actually renormalized, and it's actually the case that this is infinite. Okay, so there's a non-trivial argument there, which took us for a while to figure out. Okay, but that's the smallest of the problems. Then you have to figure out how you analytically continue. So they have analytic continuation which satisfies a certain relation, which is here. So there's an explicit function which tells you how to analytically continue beyond the Q. So you reflect in the Q. And then there is also a certain periodicity. Namely, if you shift by this gamma over 2 or 2 over gamma, then modulo an explicit factor, you have sort of periodicity. So if I take now gamma over 2 and 2 over gamma independent over the rationals, then this periodicity actually determines exactly what the function is. And that way you prove that it's given by the DOS formula.
So 2 and 3 are
2 and 3 are long stories.
a bit outside of where C was originally defined.
Outside of what? Where C?
Where the 7 bonds are true.
Yeah, so suppose alpha 3 is alpha 1 is bigger than Q, so I don't know what it is. Now I would define it. Let's define C alpha 1 to be C2Q minus alpha 1. This is now in the allowed region, times an explicit number here. Okay, and then that actually is the analytic continuation. Here are the formulas.
In the neighborhood of alpha equals Q.
In the neighborhood of alpha equals Q. And the DOS formula satisfies exactly these relations here.
Is it characterized by axiomatically then?
No. I mean, I've already went at least 7 minutes over time, and I have.
T is until 4:30.
Yes. So DOS. Here is the horrendous formula for the D and the R. Okay. And it has been long known that what does the R say? It says that somehow I can reflect so vertex operator with alpha and 2Q minus alpha modular number are the same. That's very mysterious if you have e to the if this is a random field, right? Very mysterious. This has been the biggest mystery of Liouville theory ever since it was conceived. This reflection symmetry. This is the symmetry of the DOS formula, which doesn't seem to have anything to do with random fields, okay, or anything real ordinary numbers. Let's put it like that, okay. So we prove this actually. This holds in the sense of this analytic continuation, and these numbers R and D, which from DOS are given by this formula, we get from an asymptotic analysis of this multiplicative. It's analysis how we get these numbers. Okay, and in particular, this coefficient has certain probabilistic origin in tail behavior or multiplicative chaos. So that's a long story, but at least I should flash one slide where I say that, of course, there has to be an identity somewhere. You're never going to derive such formulae unless there is some identity somewhere, okay? And that identity is something well known, which is postulated in conformal field theory, namely, there are certain particular 4-point functions which satisfy differential equations. This is called Belyavin-Polyakov-Zamolodchikov equation. I take my 3 points as before, and I put the third one with a very particular number here, this mysterious gamma over 2 and 2 over gamma, and view this as a function of one complex variable. It satisfies second-order differential equation of hypergeometric type. Proof is just take a derivative and do some Gaussian integration by parts, and a miracle happens. Things which cancels, everything cancels, and you get this equation. Of course, you would never guess this equation unless you knew that it has to be there. The reason is that these are you can guess that these should be something which in the theory of Virasoro representations are degenerate fields. And they are given by e to the minus chi times phi with this particular chi. Okay, so we have such an equation. We have equation for this guy. Why does it have something to? Why does it help us to determine the one without that? Okay, that we want to compute this guy. Huh? It helps because we can now try to take u to 0. If u goes to 0, this u matches with that, and you seem to get the 3-point function. And you have to do asymptotic analysis for that. You do it, and the story goes on. But I don't know. I mean, I should have stopped already 10 minutes ago. So let me stop now. Okay, we can.
Yeah, we can ask questions.
I can just tell you that here is a reflection coefficient. Here is another description of it, and here is a summary which says that we have sort of started the Belyavin Polyakov samological bootstrap business by proving, by getting these structure constants. And now what would be really nice to do is to continue along this lines to actually prove in this model the conformal bootstrap. Namely,
when we have many factors.
When I have a 4-point function, the bootstrap tells that it's the 4-point function is given in terms of, it's a quadratic, it's an expression in terms of these structure constants and certain universal functions, which are, it's completely explicit. So that would be really nice, and I think it's sort of not impossible to imagine that one could actually do it in the Liouville model, because this is so, sort of seems to be.
I thought somehow from your earlier statement that having the C of the alphas, that then you could go ahead and use the conformal bootstrap with that and get everything. But
right.
Not for the Liouville theory?
Yeah, if I knew what the spectrum is. Of course, the spectrum is, I know what the spectrum should be, but I should be able to, in order to prove the...
It's a completeness question. Right?
It's a completeness question. What the bootstrap is really is that you have to find a complete set of states in your Hilbert space, the physical Hilbert space, which you can construct here by Osterwalder-Schrader. You can construct a Hilbert space. You need to find a complete set of states. They are basically eigenfunctions to the Hamiltonian. And there's a conjecture what they should be, but
so your E to the I alphas.
They are supposed to be this.
Supposed to be the complete set.
That's supposed to be the complete set.
But at least for the subspace generated by them, then you have.
Yeah, but that doesn't.
Bootstrap, I guess.
No, because you have. Well, how does it go? You have a 4-point function. You have 4 points.
Yeah, you pushed out that.
Yeah, so phi, 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 and you put in between here complete set of states. Okay, so here you put 1 equals sum over. Let's put it really like that. Okay, then I get into the 3-point functions. The spectrum is continuous, so this is actually an integral, but basically that's the idea of bootstrap, that I put this thing and I get this in terms of quadratic sum of product squares of the structure constants.
So you would get integral.
It's an infinite sum.
It's an integral actually, so that's
So you get an integral representation.
the integral of d dp. Let's put integral of d alpha in q plus ir. And then certain explicit factors times 3-point functions. Okay. This thing is very explicit. People have computed these things numerically from this formula. Everything is explicit. It gets very cumbersome after the 4-point function when you want to do 5 or 6 or whatever. Okay, but that's not the issue. The issue is whether it's in principle. You can prove that this actually is true. Okay.
And the point is that even if you're looking at correlation functions of e to the alpha phi, as soon as you have 4, then you're not sure that you can reduce it to the 3 points.
No, you're not. There's
But numerically, it checks out.
numerically everything checks out. What is even more surprising is that you can, more fantastic is that you could do this so that you sort of fuse these two together, like I did here, or you could fuse these two together, and then you get sort of two different quadratic expressions in the structure constants. You get quadratic equations for the structure constants. These are the equations what Liouville, Polyakov, and Zamolodchikov actually solved for the minimal models. They got explicit solutions. People have studied numerically those things for the Liouville model, for conformal field theory in general. And if you take a spectrum like in Liouville theory, then the DOS formula structure constants seem to be the unique solutions of those equations, numerically, okay? So there is a lot of evidence that this certainly has to be true, okay? But it's also would be very interesting to analytically continue in gamma, because when gamma becomes purely imaginary, then the Liouville central charge becomes less than 1. It was 1 plus 6 q squared, and q becomes imaginary. Those are the conformal field theories we are used to. So for instance, it's conjecture that the FK Potts models can be described by the Liouville theory. Not the minimal models. The minimal models are not the limits of Liouville theory. They are separate. I mean, the minimal model, Ising model C equal half corresponds to certain gamma for the imaginary gamma for Liouville model, but that's a different theory, apparently, numerically again.
So you have, on the sphere, you have a multi-parameter set of conformal field theories which are well above C equals 1, right?
Yeah, there's the universal conformal field theories, okay? And it seems that there is a nice, great structure for C between 0 and 1.
Right.
And then there, in the complement, there seems to be only Liouville. Actually, there is bootstrap, numerical bootstrap.
So you're saying, is it conjectured that any conformal field theory with C bigger than 1
is
falls
Liouville.
into this category?
Falls to Liouville or some sort of
Descendant.
combinations, sort of independent combinations. Liouville plus some finite degree of freedom thing. So there's a numerical. You can numerically look at the bootstrap equations and look for solutions, and it seems that all the solutions are given by just Liouville. So there's Liouville and the minimal models, and then okay.
Well, aren't there like a bunch of superconformal?
There are super conformal field theories for C less than 1, for instance.
Did you look at those at all?
No. I'm not claiming to know.
Don't they have C bigger than 1 though? Or,
Yeah, you have, for instance, not even super conformal. You can have Wessumino Witten models. Yeah, they have C bigger than 1. Yeah. So there are points, other points in the C bigger than 1 region.
So how is that consistent with the picture you were just discussing about?
Generically, in the C bigger than 1, you have only Liouville. I think that was the claim.
What happens in higher genus?
Higher genus. Right, in the higher genus, of course, if you take this two-dimensional gravity point of view, then you're supposed to integrate not only the conformal factor, but also the moduli. Mm-hmm. So you have to do the integral over the moduli space. And when you take the free field on the, I mean, if you if you take the Liouville model corresponding to gamma equal to 2, then you can sort of do this. This was done by Rod, Vargas, and who was the third person? Anyway, so you can actually look at how the modular space integrals diverge. The problem is that the integral over the modular space is otherwise okay, except that you have the singularities. You could have singularities on the boundary, and that you can study. You can study how this Liouville what comes from the Liouville model, how it behaves on the boundary. And it actually turns out to be integrable at the singularity, at the boundary. So these integrals in that case exist. And in some sense that case should be the most singular case, but that's the only case where things are sort of explicit, because you have to for Ising model, I don't think it's probably not known in arbitrary genus how the Ising partition function depends on behaves on the boundary. But in the free field case, you know it, because the determinant of the Laplacian can be studied.
Okay, well, Antti, thank you very much.
I'm sorry.